Hello everyone, my name is MD Mursalat Islam Pallab from Department of Computer Science and Engineering at Dhaka International University. I am presenting this work on behalf of all four co-authors, myself, MD Ashraful Mullah, Rashiduzzaman Rakib, and our corresponding author, Dr. MD Abdul Basit. Our paper is titled AI-Driven Prescriptive Analysis for Hybrid Learning Mode Optimization, a multi-model benchmarking and explainable AI framework. Agenda. Here is a quick roadmap. We will go through the motivation, our contributions and dataset and features we engineered, our 5 model benchmarks and prescriptive counterfactual engine, explainability results, statistical validations, and finally some practical guidelines for institutions. Why hybrid learning needs personalized guidance? Let's start with the problem. Since COVID-19, hybrid learning has become the norm, but that's made more selection decisions more harder for educators and administrators. Most existing research studies online versus offline effectiveness only at the population level. It tells us what works on average, but it completely misses individual variability. So the real question we wanted to answer is much more specific. Given this particular student with their study habits, focus and retention profile, will they perform better online or offline? That's the gap our work addresses. Contributions. We make 4 contributions. First, a feature engineering protocol that builds interaction trends, a retention efficiency index, and a focus to study ratio on top of the raw behavioral data. Second, a 5 model benchmark, random forest XGBoost, Light GBM, SVR, and MLP, evaluated under consistent cross-validations, where Light GBM comes out on top. Third, a counterfactual simulation engine that generates a personalized mode recommendation for every single student. And fourth, a fully explainable AI layer using shape, line, and partial dependence plot, so every recommendation is transparent and auditable. Dataset. We used the online versus offline learning performance dataset from Kaggle. 1000 anonymized student records, perfectly balanced 500 by 500 between online and offline. It covers 5 subjects, study hours from 1 to 8, retention and focus scored from 80 to 100, and exam score as our prediction target. We used an 80 by 20 train test split with an fixed random seed of 42 for fully reproducibility and standard scaled all 9 features. Feature engineering. Raw study hour along turned out to be a weak predictor, so we engineered 2 key interaction features. The focus to study ratio captures cognitive engagement per hour studies, not just raw time. The retention efficiency index blend memory retention with attentional efficiency, again normalized by study time. We also added 2 multiplicative terms, study time retention and focus time retention. The core insight here is simple. How a student studies matter far more than how long they study. Framework. Here is the end-to-end pipeline. Behavioral data flows through feature engineering into our 5 model benchmark, which selects Light GVM as the prescriptive engine. That engine then runs a counterfactual simulation, scoring every student twice, once under each mode, and finally passes through our explainable AI layer with safe line and PDP. Benchmarking. On a held-on test set of 200 students, we compared all 5 models. All of them achieved an R squared above 0.92, which already tells us our feature set is capturing the right signal. But Light GBM stood out with the best R squared with 0.951 and lowest RMHE of 2.948, edging out Random Forest with XGBoost and clearly outperforming SVR and MLP. Results. So why Light GBM? Test R squared of 0.9508, RMH of 2.948, and a 5-fold cross-validation R squared of 0.946 with very low standard deviation, meaning the model is stable across the data partitions. This also confirms a border pattern from tabular learning literature tree assembled to outperforming kernel methods and neural network on structured data like this, and they are efficient to train and deploy, which matters a lot for real world decision support system. Prescriptive analytics. This is where we move from prediction to prescription. For every student, we take their profile, set their learning mode to online and predict a score, then set it to offline and predict again, holding every else fixed and recommend whichever mode gives the higher predicted score. This counterfactual design isolates the causal effect of the mode itself, independent of the student's other traits. A great outcome. Across all 1000 students, the engine recommended online for about 53 and offline for about 47. So neither mode dominates, which tell us there is no systematic bias in recommendations. The mean optimized score only rose slightly from 71.675 to 71.753. That's near zero gain isn't a weakness. It actually tells us the original dataset was already close to an optimal mode allocation. Subject level prescription. Breaking this down by subject is more revealing. English and history consistently benefit from offline instruction. These are reading and context retention heavy subjects that favor face-to-face settings. Programming and math shows small gains under online delivery, which makes sense given how mature asynchronous digital tools are for computational subjects. Explainable AI. Moving to explainability, we used SEP to understand what actually drives these predictions. The focus time retention interaction terms dominate in both modalities, with a SEP value of 8.26 online and 9.85 offline. That higher offline value suggests the classroom environment actually amplifies the benefit of strong focus retention alignment, which has real implications for how we designed learning environment. Explainable AI, LIME and PDP. At the individual level, LIME gives us plain language explanation. For example, for one student, we can say their retention focus synergy is low online, so they are expected to improve their structured classroom engagement. Our partial dependence plot also show that predicted score rise steadily with retention score in both modes, but the offline slope gets noticeably steep for higher retentive learners. And interestingly, the study hour curve patterns out beyond about 5 hours, a genuinely practical insight for advising students on time management. Statistical validation. To validate all the results, we run a paired t-test comparing scores before and after all recommendation. The improvement was small, plus 0.078 points, with a non-significant p-value of 0.28 and a small cons of 0.034. So statistically, this confirms the original allocation was already well balanced. This isn't a failure of our model; it's a property of the dataset. What this really tells us is that our framework is most valuable for identifying individual students who benefit from switching models rather than producing large group level gains. For institutions, so what should hybrid learning administrators actually do with this? Favor offline delivery for English and history, learn slightly online for programming. For math and science, decide on a per student basis since the variance is too high for a blanket subject level rule. As a cross-cutting principle, use a composite focus retention index as a leading indicator. High scorer will succeed in either mode, but low scorer are generally better served offline. Conclusion. To summarize, we build a reproducible, interpretable decision support framework that unifies predictive models, counterfactual prescription, and explainable AI in one pipeline powered by LightGPM. The focus retention interaction is the strongest driver of outcomes across both models. The English and history learners are best served offline, and programming learners slightly online. For future work, we plan to extend this to multi-institutional, longitudinal data and socioeconomics and technology access features, and explore real-time adaptive recommendation. These are our key references. Thank you very much for your attention. I am happy to take any questions.